The assumption we make about the diaphragm being much more flexible out of plane than the supporting members, and the approximation that each diaphragm panel behaves independently, mean we can determine how pressure on the diaphragm transfers to the supporting members. Let's take a look at a strip of diaphragm from our example floor with uniform pressure. Because of our assumption and approximation, we treat the strip as simply supported, uniformly loaded members. If you apply moment equilibrium, you will calculate that half of the load on an individual member is carried to each end. If we draw a dividing line halfway between each support, the load between the support and the dividing line goes to that support. Another way of saying this is that the load goes to the nearest supporting member. That is not another assumption. It is an outcome of the assumption and approximation we already made, and it is really helpful to recognize. Supporting members might be beams, girders, joists, or trusses. It doesn't matter what the member looks like, just that it connects to the diaphragm and holds the diaphragm up. In the last video, we talked about diaphragm panels. A panel is the piece of diaphragm between supporting members. So if we look at a plan view, that is, from above, of the diaphragm and supporting members, envision each supporting member as a dividing line between panels. Therefore, this example floor has 3 panels. Some diaphragm panels are only supported on 2 edges, and those edges are on opposite sides of the panel. Because the load can only travel left-right to reach a supporting member in this example, we call this a one-way diaphragm, or that the diaphragm is experiencing one-way action. Load goes to the nearest member when the diaphragm is experiencing uniform load. So we can draw dividing lines that show which part of the panel surface sends load to each supporting member. For a panel experiencing one-way action, the dividing line is halfway between the supporting members. For a rectangular panel, that dividing line is parallel to the supporting members. If the panel is not rectangular, the dividing line is still halfway between the supporting members. Most diaphragm panels are supported on adjacent edges, on 3 edges, or along all 4 edges. For these situations, we call the panel a two-way diaphragm, or that the diaphragm is experiencing two-way action. Load still goes to the nearest supporting member, but because there are members on adjacent edges of the panel, the dividing line starts by bisecting the area between the supported edges. Load on this piece of diaphragm will go to this supporting member, and load over here will go to this supporting member because it is closer. If we draw the bisecting lines from each corner, notice that these two meet at a point. On the other side, these two meet at a different point. Between those, the areas closest to each supporting member are identified by connecting the two meeting points. This piece of diaphragm is closest to this member, so load on this piece comes to this supporting member. On the other side of the dividing line, a piece of area is closer to this supporting member. If our diaphragm panel is rectangular and supported on all 4 sides, the dividing lines will result in 2 triangular regions and 2 trapezoidal regions. The triangular regions will be closest to the shorter supporting members, and the trapezoidal regions will supply load to the longer supporting members. Load can only travel to supporting members. So if we have a diaphragm panel supported by just two adjacent members like this, we draw a dividing line that bisects the angle between the members. All the load in this area must go to this member, and all the load in this other area must go to this other member. Similarly, if we have a panel supported on just three sides, we follow the same process. Draw bisecting dividing lines from the corners where adjacent members meet. The shorter members will support triangular regions, and the longer member will support a trapezoidal region. Sometimes we have a panel supported on adjacent sides, and that panel has a large aspect ratio. When I say aspect ratio, I mean the ratio of the length or span of the longer side divided by the length, span, of the shorter side. In this case, when we bisect the corner angles, we get small triangles at the ends. When we connect the peaks of the triangles, we get trapezoidal regions that are almost rectangular. If the aspect ratio is sufficiently large, we typically approximate the diaphragm panel as acting one way in the short direction. So we are saying all of the load goes to the longer members and none goes to the shorter members. So what is sufficiently large? Common practice is to consider 2 as large enough to approximate the panel as acting one way. To be clear, this only applies to panels supported on more than two sides. That is because the one-way action needs to be between supporting members on opposite sides of the panel. So how reasonable is this approximation? For an aspect ratio of 2, if we calculate the peak moment in the long member treating the panel as acting two-way, and we calculate the peak moment in that same member treating the panel as acting one-way, our approximation only overpredicts the moment by 1%.